सॉरी सर, वो मीटिंग थी कुक की, वो चल रही थी अभी।
अच्छा,
2 मिनट तो वो कमेटी आई हुई थी जी। तो और से ठीक है सर।
अस्सलाम वालेकुम।
वालेकुम सलाम डॉक्टर साहब, थैंक यू वेरी मच। So let us start the in the series webinar series of the artificial intelligence. Today the speaker is Dr. Masroor Hussain. He is an associate professor at GIK Institute, Topi. Dr. Saab is working as associate professor there. He had obtained his first professional degree in computer science from FAST Lahore. After completion of his BS, he did MS with the specialization in artificial intelligence and then obtained PhD degree from GIKI. His research interest includes adaptive meshing, data mining, data warehousing, finite element methods, neural networks, parallel computing, and other titles. He also worked in industry as a software engineer. He spent 2 years in NUMT, where he developed the software for medical instruments. These instruments read the neuromuscular movements of the human body and analyzed them. So after successfully defending his MS thesis, he joined GIK Institute from June 2004 as research associate, and from that time he is in GIK. So today he would like to speak on high performance computing and its utilization on deep learning models. So Dr. Saab, over to you.
Assalamu alaikum everyone. I am very thankful to Pakistan Academy of Sciences and Qaeda University to give me an opportunity to give a brief talk about high performance computing and its utilization on deep learning models. So before starting my talk, first I would like to show you about the top 5 high performance computing in the world. There is a website you should know, that top500.org, that maintains the top 500 supercomputer around the world. So based upon the teraflops, it ranks different supercomputers in the world. Right now, as per November 2021 ranking, the top supercomputer is in Japan. It is developed by Fujitsu Siemens. So it has processor A64FX, that is 48 core. And for the interconnection, it is using Tofu Interconnect D. Well, this is interconnection networks, so how we can connect multiple computers. For example, in your daily life, we connect computers using Wi-Fi or Ethernet. So this is a specialized network topology that used for high performance computing, because it helps to have multiple connections at the same time. The second supercomputer is named is Summit, that is in United States, that is developed by Oak Ridge National Laboratory, and that is IBM based supercomputer. It is using IBM Power 9 processor, that is 22 core, and it is accelerated using NVIDIA Volta GB100 GPU. The third computer is also in United States, that is also developed by IBM. The third one is Sunway Taihu Light, that is in China, that is developed by National Supercomputing Center in Wuxi, China. And the fifth one is United States. So based upon the data of top500.org, there are a lot of applications those can be solved. These supercomputers not solve atmospheric problems, and other problem related to physics, biosciences, chemistry, air defense, and electronic engineering, mechanical engineering. So we have a lot of applications from all engineering and sciences domain. Now the question is how we can get help from HPCs. Due to the emergence of fast accelerators in the last 2 decades, the HPC has a lot of applications in robotics, and based upon its acceleration speed, deep learning, deep neural networks have emerged a lot. That is not a new concept. Actually, deep learning neural networks are here with us since 1980s. But based on the available processing, so we can see a lot of people are using deep neural networks either in biology, physics, mechanical engineers. All of them are using these network for predictions. So before going to HPC, first we should know what kind of computation facility we can have right now. Based on Flynn's taxonomy, we have 4 kinds of computers. Those exist. The first one is single instruction, single data stream. Then second one is single instruction, multiple data stream. Third one is multiple instruction, single data stream. Fourth one is multi-instruction, multiple data stream, that is MIMD. In MIMD, we have 2 kinds of computer. One is shared memory system, second one is distributed memory system. So what is SISD? Our traditional computer normally belongs to traditional computers like PC and old mainframe. All of them belong to this SISD architecture. It doesn't mean that we don't have parallelism in SISD, but we can have parallelism in SISD by the introduction of your IO processors, your pipelining, that concepts have been used. The second one is SIMD. So SIMD nowadays very famous due to GPU. And so all array processor belongs to this category, like FPGA and other accelerators available. All of these accelerators belong to this SIMD category. Then we have MIST. MIST stands for it try to solve multiple instruction on single data stream, but technically we don't need those type of computers. So far we don't have practical implementation available, but theoretically the category is available and defined by Flynn's. Finally, we have another category, that is MIMD. In here MIMD we have 2 types of high performance computing available: shared memory system and distributed memory system. In distributed memory system, you have probably heard the name of cluster and grids, and those belong to distributed memory system. And then for shared memory system, we have multi-core systems. Right now, everyone, even on our handheld devices, mobiles are multi-core systems. So most of time in your even mobile, we have GPU and multi-core system. So if your application knows how to use these 2 processors, you can easily optimize the working of your applications. So now the question is how we can do the programming. So to start with, first I will go for shared memory system. In shared memory system, there is some, okay. Okay. So for shared memory system, we have multiple CPUs. Those are connected to your main memory using some network topology. That network topology can be of anything. Like I have told you, for interconnection, you have seen top 5 computers. They are using different kind of interconnection. So here we can use any kind of interconnection. So most of the time we use bus architecture. That is a cheap way to implement networking. Even your Ethernet is using bus architecture. So whenever you are going to purchase some computer, if either Intel machine, AMD machine, you see there is written FSB, that is front side bus. So that topology they are using. So in different vendors have implemented different network topologies to improve the performance of their multi-core CPUs. In distributed memory system, we can say I have 4 laptops and I would like to implement a program or run a program on these 4 laptops. And the question is how I can connect. You can connect it using Wi-Fi, Ethernet, or some other network topology. Then you can connect them and you can improve the performance of your program. But the question is how you can do the programming. In shared memory system, the best way is to do programming using multi-thread programming. Multi-thread programming is not easy for you guys, or is simple programmer. So now, as a scientific community, we have a framework that is commonly known as OpenMP. So by using OpenMP, you can easily optimize your codes using multi-core systems. So OpenMP mostly supports C, C++, and Fortran language. For distributed memory system, the question is how you can do simple programming. If you go for the traditional programming methodologies, you can easily implement using socket programming, but that is a very difficult way to implement your code, and that is very difficult to scale. So for the scalability part and for easiness of the programming, now we have a framework that is available for the high performance computing. The standard is known as message passing interface. Now MPI is a standard to work with distributed computing system. In SIMD architecture, the third high performance computer category is SIMD architecture. In SIMD, all GPUs belong to this category. The difference between SIMD architecture and simple CPU unit or MIMD processor is the difference of the control unit. In normal, your CPU, we have processing element plus control unit. But in GPU, we don't have a control unit inside it, but we are using, for the control unit, we are using CPU, and for the processing, array processing, we are using GPU, or you can use FPGA and other accelerators based on the vendors are available. Like Google gives you tensor processing units, and you can use them for the to improve the performance of your neural networks. So that is the main difference between SIMD and MIMD, the global controls unit. So right now at GIK, we have 160 core HPC system that that consists of 4 system, 3 slave nodes, and 1 master node. Master node consists of 64 core machine that is using AMD architecture, and 3 slave nodes are using 32 core slave nodes. So I and Mr. Shakir are managing that system. So for MIMD shared memory system, I have talked a little about it. The best to do is programming is using process-based, or you can, shared memory system. For process-based, you can use fork weight, and for thread-based, you can use pthread library or Solaris thread or any library. For example, in Windows, if you are doing programming, you can use Windows threads. In Java, you can use Java threads. But the question is how we can do the synchronization. For synchronization, in shared memory system, we have to synchronize using read and write commands. So the difference between shared and distributed is the synchronization part. In synchronization at shared memory system, we are using read and write, while in distributed, we have to use send and receive. So that's why I have told you we have a specific framework that is message passing interface. So to do programming using process-based and thread-based, that is very difficult. So what you can do, you can do programming using OpenMP. So there are different pros and cons to discuss about programming on threads. You can read these base papers. Those are imperative concurrent object-oriented languages, and then threads cannot be implemented as library. So OpenMP technically is a library-based solution. Now the question is how we can do programming in shared memory system. Either by the introduction of new parallel or concurrent programming language. As a simple user, it is very difficult. We learn first the sequential language, C or C++, then learn a lot of other languages, and then we try to learn different parallel languages. So the learning curve will be very slow, the productivity will be very slow. So that's why not, instead of concurrent language, we should have some solutions using library-based solutions. So we just include that library and do the programming on our existing sequential programming language, because we know the syntax, we know, and we are very familiar, and we can easily write the programs using sequential language. So OpenMP is providing the library-based framework. There are some issues if this is using threads. There are some issues if we implement user thread library. So instead of user thread library, we can use some. So we have to inform your kernel so we can optimally use threads and multiple processors. For distributed memory systems, the traditional way to do programming is the socket programming that I have told you. You have to open a socket and then send data, and on the receiver end, you receive the data. The problem is it has limited group communication, it has bad performance, and the major problem is the scalability. For example, if I have written down the program on 4 processors, let's suppose 4 machines. For example, the laptop at GIK, so I can say GIK 0, GIK 1, GIK 2, and GIK 3. So what's about if I would like to run the program on QAU 0, QAU 1, QAU 2, and QAU 3. So what I have to do, I have to change all the IP addresses. So that is very difficult as a portability. And for example, if I would like to scale up for the 8 cores, what I have to do, I have to rewrite the code and I have to embed their IP addresses. So that is not a good way for high performance computing. So the scientists have initially come up with a very good library environment that was a parallel virtual machines. You probably know, or you probably have heard the name, that PVM. That is a very good implementation available, and that was a portable. Now it is obsolete, and now all the programmers of PVM are shifted to message passing interface. MPI right now is a new standard. So it has 2 standards, MPI 1 standard and MPI 2 specification. So why people are shifting to MPI? Why? Because we have both types of implementations available: vendor-based specific implementation and open source implementation are available. Vendor, for example, if you had seen the top 5 computer, some vendors are from Fujitsu Siemens, some vendor IBM, Dell, Intel. So all types of implementations are available, IBM and Fujitsu Siemens, and even open source is available, you can use that. So this is the standard because it supports all the platform. You can do programming, MPI programming on Intel machines, AMD machines, IBM Power PCs, Fujitsu Siemens. So just you need to include 2 libraries. If you are doing programming on C, C++, you just need to include MPI.h, and for Fortran, you just need to include MPI.f, MPIF.h. So, and main thing is, as a programmer, the functionality value. Whatever we think, what kind of parallel communication I need to do while converting my sequential code to parallel code, you just need to read the manual and just make that call to a function. That is very easy. So you can easily do it. And one thing, for the portability, you do not need to modify your code. If you have written the code in standard C, that will run on your Mac PC, even run on your Linux machine, your Windows machine. You don't need to do anything. And for the scalability, this is another major advantage of MPI. We are doing the communication based upon process IDs, not the IP addresses. So you can scale it. Just need to say, run that program MPI run -N8. So it will spawn 8 processes on different computers. If I say MPI run exec -N16, so it will automatically run that program on 16 processors. So that is very easy to scale. Just you need to change the parameter. So we can say MPI is large because you have to learn 125 functions. MPI is small, you just need to learn only 6 functions. Technically, I would rather say that is the right size based on use. For example, most of the times I am working on computational scientist. Probably I need to learn only 10 functions or 12 functions, no more than that. As a data scientist, probably you need to learn 15 functions, no more than that. So it is the right size. It depends upon your utilization. You just need to remember those functions. You can easily write down the programs using MPI. The major question is, when we are converting the sequential program to the parallel program, the thing is you have to partition the problem in such a way that your problem can be solved concurrently. There are 2 methods exist to solve problem on parallel machines. One is data partitioning, the second is functional partitioning. Functional partitioning means based upon different function. For example, there in some part of your code you are adding something. In some part of code you are multiplying something. So you can say addition can be done in this one computer, multiplication can be done on simple computer in another computer. So that is a functional partitioning. What is data partitioning? For example, I am an instructor, I have 4 TAs, I would like to mark papers. I have 100 papers. What can I do? I take 25 computers and give 25 computers to my other TAs. So that is a data partitioning. I give some data to tier 1, tier 2, tier 3, tier 4, and 1 to me. So if I also mark the papers, so there are 5 instructors, so if I divide it, so everyone will get 20 papers. So that's how we can divide the data. So based upon data partitioning, we have different data structures and algorithms are available. So most of time for scientific computing, we can use spatial data structures. Why spatial data structure? This because in scientific problems, we are dealing with spatial information because we have the data. For example, if I talk about bridges, aeroplanes, we have spatial information of the structure that we are trying to solve in X coordinate, Y, and Z. So best thing is to do with spatial data structures. However, in the case of computational part in deep learning, we are mostly dealing with graphs. So I can make a graph of, I can represent a problem into some graphs and then cut that graph into K partitions. For example, the K partition can be 4. Why 4? Because I have a 4 machines. I can give one part to the processor computer 0, second part to computer 1, third part to computer 2, and fourth part to computer 3. So that's how you partition the thing. So basically, the algorithms used for spatial data structure, mostly people are using quad tree, octree, orthogonal bisection. What is quad? Quad means 4. For 2D data, we use quad tree. For 3D data, we can use octree. So, and most of advanced software, if you are just using, you just need to select those partitioning methods. You don't need to implement it by yourself as a scientist. Now, if we talk about just specifically we come up with deep learning. Actually, the question most of people say, what does deep mean? What is the meaning of deep? How much deep we have to go? These are simple MLPs or simple machine learning algorithms. But the thing is, we have a lot of connection. We are dealing with a lot of data. So based upon the emergence of new supercomputing facilities available, nowadays we are able to solve a lot of data and a lot of equations. So based on the application, we have different implementations available for MLPs, neural networks. So the first example you probably know, that is convolution neural network. What is the difference between convolution neural network? This is a subtype of MLP, but instead of applying matrix multiplication, you just need to replace with convolution. So now the question is, as a computational scientist, how I can improve the performance of my deep learning algorithms. I have to smartly implement these matrix multiplication and convolution functions. So because if you know about the neural network architecture, we have layer to layer architecture. We send data from one neuron to other neurons and so on. So you probably have heard the name of tensors. So that's why Python gives you a framework, give you a tensor flow, because we are flowing the tensor from one state to another state and so on. So you can implement. First time, the convolution neural network is not a new thing for us. The first time it was developed in 1998 by Yuan, and it was earlier known as LINAT. So normally whenever we talk about convolution neural network, if you are dealing with signal processing, image processing, most of people are using convolution neural networks. So here we have convolution layer, ReLU layer, pooling layer, and fully connected layer. So based upon your application and based upon the literature review, you change the architecture. So other deep neural network name you probably know, that is RNN, and a special case you probably know, it's a long short-term memory networks, that is also known as LSTM. There are some problems with RNN. Basically, that is a major problem, that is vanishing and exploiting gradient. What does it mean? As a computational scientist, I just say, not as a data scientist. Computational scientist is say, for example, if we multiply two numbers, what will happen? If I multiply two numbers and both numbers are less than 1, for example, 0.25, 0.25, take multiply. So next number will be less than 0.25. And after 4 or 5 or 6 multiplication, it will approach to 0. So that is known as vanishing gradient. And what's about exploding gradients? Why? For example, if I have a large number, after some multiplication, I cannot store in my long variable, double long, I cannot, long double, I cannot store it. So in order to avoid that, so we have to use something else. For that purpose, scientists have come and approached to forget some units and used addition operator instead of simply just using multiplication operator, and that's how they have evolved their RNN concept to LSTM. So you can use that problem when we have temporal information available in your problems. For example, a classical example, if you see type in Google, so they are using long LSTM, classical Google autocomplete. So there is another thing probably you know, that is generative adversarial networks. So here we have generator model, and we have some real example, and we have some fake examples, and then we generate something. This probably you have heard the name of the person does not exist. The person does not exist. So they have generated a lot of fake images. Those persons don't exist in real life. So you can use GAN. So obviously in all these neural networks, we need a lot of connection. We need a lot of matrix multiplication or convolutions. So thing is how we can improve the performance, because in all these things, if you see, even in MLP, you need to implement matrix multiplication. Once you know the algorithm to improve the performance, you can improve the performance of all of your machine learning algorithms. So if you recall Flynn's taxonomy, the best taxonomy that you recall, that is SIMD taxonomy. There I had written that it is also known as array processors. So all array processor belongs to that category, because if we talk about matrices, tensors, at the end, these are the set of vectors, arrays. So you have, if you implement a method to increase the performance of single array or vector, you can increase the performance of your tensors operations, matrix operations, and you can implement your CNN. So there are other deep learning algorithms available. Radial basis functions, the difference, this is also a type of MLP, but instead of simple activation function, they are using radial basis function as activation functions. Then we have other examples available: restricted Boltzmann machines, autoencoders, deep belief networks. Basically, they are using belief Bayesian networks. There is another algorithm that is SOM, self-organizing matrix. So you can say that that is also can be a deep. But the question is how you can implement it. There are different implementations available. You can use PyTorch framework, TensorFlow, Keras, MaxNet. There are a lot of other frameworks available. Tino, you can use it. But for the easiness and of the programming, because deep learning neural networks, MLP, are being used by different scientists, not as computer scientists. People are using these machine learning algorithms in mechanical engineering, materials engineering, in biomedical, medical science. So the thing is, we need to provide the interface so they can easily learn to do the programming. They have the data. They just need to see how the data behaves. For that purpose, we have a lot of implementation available. PyTorch, so it is very good because it is using also GPU accelerator to improve the performance. Then underlying all types of deep learning neural networks are available. You can implement. There's a TensorFlow that is also an open source deep learning framework that is also supported by Google Colab. I will talk about in the next slide. And TensorFlow, then we have Keras, that is also a Python based language, but the thing is Keras is a high level and this is a low level. If you like to improve the performance, okay, then you should use TensorFlow. If you, as a normal scientist, you are a biomedical and you just need an easy implementation, you can just use Keras. In underlying Keras, you can change the lower layer. Either you can use TensorFlow, you can use Microsoft Cognitive Toolkit or Tino, whatever you can easily use. There is another thing that is MaxNet, and that is also supported by NVIDIA and GPU. That supports NVIDIA GPU. You can, if you have NVIDIA GPU, you can do, or you can use MXNet. So one more thing, MXNet supports both symbolic programming and imperative programming. As a normal user, actually, I am a programmer. I use, I download Python, C programmer, C compilers, and do the programming in VI. That is not easy for the simple programmer. Okay, so what you can do, we need to have some easy tools available for the people. So one thing is you can use Jupyter, you can easily install, and the other one I recommend that as a startup or simple scientist, you should use Google Collaborative Lab, that is Colab. It is known. It has 3 different licenses available: simple Google Colab and Google Colab Plus and other professional Colab Plus. I don't remember exactly. So based upon the your computational facility, you can use different licenses. The base Google Colab is free for you guys. The beauty of Google Colab is that it supports 3 things: your normal CPU, your GPU, and it also provides you TPUs. TPU stands for Tensor Processing Unit. So you can change the underlying processor by using runtime. So just, I have given you an example. If I select GPU from here, runtime, I can select TPU, and whatever you do the programming on PyTorch, or you can do programming on TensorFlow, Keras. Once you select it, just simple thing. All computation will be done on GPU if I select GPU. If I select TPU, all computation will be done on your TPU. These are your accelerators. These accelerators belong to SIMD architecture. There are other accelerators available. You can enhance the performance using FPGAs. So any questions? I think that's all for the today's talk, because I was given 30 to 40 minutes. If you like to have some talk about the programming, how you can implement it, then we can have separate sessions for doing programming on GPU using CUDA. And for MPI, we need, I can give you other lectures on MPI, how can we do the programming on MPI. We can have separate lecture on OpenMP, how we can do the programming on OpenMP. OpenMP is a framework and standard for doing programming on shared memory system. MPI is a standard for doing programming on distributed systems, and CUDA is for programming on media system. The one thing, last thing you should remember, whenever we are working on machine learning algorithms or deep neural networks, we have to use, or we have to combine MPI and GPU accelerators programming. Why? Let's suppose I have 2 computers. In one computer, I have GPU. Second computer, I have GPU. But I would like to solve the problem using these 2 computers' GPU. How I can do? First, I have to distribute the data. Distribute one part to one computer, the second part to another computer. And then we can use those GPUs. So mostly you have to combine MPI and GPU programming. So as a data scientist, I recommend that you should know all these parts. Even I went to Urbana-Champaign, I have seen that their supercomputers were headed by civil engineers. So I think everyone can do easily programming on MPI and GPU. Thank you.
So thank you very much, Dr. Saab, for the interesting lecture. So any questions from the audience? Please. So is there Nazir?
Sir, Dr. Muazzam here, sir.
Yeah.
Sir, and thank you so much, sir, for the nice talk. I have a question regarding the metaverse that recently introduced by the Facebook. So what is the role of supercomputer? Yesterday, I have studied another problem that in that metaverse, you wouldn't be able to show the lower limb of those people who are actually trying to grab the opportunity over there. So the processing power is enough to provide them the upper limb means sketch of their body, but not the lower limb because of the computing power. This is just published day before on BBC as well.
Actually, the modeling, the problem is that whenever we model some problem, okay, we have to mesh it. For the accuracy part, you have to go for fine meshing part, because for fine meshing you have a lot of data, and the thing is that how much data your supercomputer can store and how much equation it can solve. So based upon the available supercomputer, probably they have come up with the idea that these supercomputers cannot solve. For example, it might be more than 7 million processors. So what we can do? So it all depends upon your available computational facilities. So either you
Yeah,
have
so
to
actually
compress
the
the
question is that
either you have to compress the problem, you have to come up with new models, or you have to solve using these supercomputers. The best thing is you have to do some research and compress the model, and that's how probably you can solve those computational intensive or data intensive problems. So I have not worked on exactly those equations. Probably we have to think about, and we can, if we model the complex multiple neurons and we can represent in the single equation. So that's how probably we can improve the performance. Or
yeah,
probably
exactly. But I actually is looking into AR and VR as well, and the computing power over there are increasing with a very fast speed. Though we have the speed mismatch problem earlier, if we have a look into the computer generations, but now if we look at the requirement of the modern world, then the computing power is not going to match or to address those problems.
Yeah. One more thing, the best thing, because I'm director of ICPC, I have seen and we have talked to some Google machine learning guy a week or 2 weeks ago. What actually they are doing, they are just need a model that can easily classify 80% of data. More than 80% is overkilling most of the time. The best thing, first you have to find out the simple algorithm. If you have the algorithm, that is the fastest way and the accurate way to solve the problem. Then you go for the machine learning. That is not a good idea for the market, that you just apply machine learning. Machine learning normally they apply to enhance their capability. So first thing, as a good scientific engineer, we should find out that model that can compress the things and then try to solve. Just not, if we don't have any model, then we can say we should solve it. But it all depends upon the scenarios.
Right, sir. Thank you so much. I have also shared the document which shows the 7 challenges for this metaverse recently introduced. So it might be helpful for the audience as well. Thank you so much.
So, anyone else for the questions? So if no, then thank you very much, Dr. Saab, for interesting lecture, and I am grateful on behalf of us for the interesting lecture, for your time and interest in the affairs of the Pakistan Academy of Sciences. So thank you very much for your kindness, for sparing time out of your very busy schedule. So with that, I would also like to thank all the participants, especially the Dr. Khalid Mahmood Khan Sahab and Dr. Noor Muhammad Bhatt, and all other fellows and members, including Dr. Mazam Ali Khattak Sahab, for their presence, and hopefully they will also participate in the next lecture of this series. So thank you very much for all who are either present physically or present virtually. So along with that, this is the end of the lecture, and hope we would like to continue this webinar series, and everybody is interested to participate into it. So thank you very much, and Allah Hafiz.
Thank you so much, sir. Thank you, Dr. Masroor, for your time and a nice lecture. Thank you. Allah Hafiz.